So this is going to be our next four-step process. This is chapter 10. And so this is going to be a generic four-step process for, this is a confidence interval for difference in proportions. And this is chapter 10. I don't have my folder in front of me that shows which number we're on, but you should probably know which number. If not, I'll tell you on Monday. So generic four-step process for confidence interval for difference in proportions. So it's a confidence interval, not a test. It's proportions, not means. This is the only part that's different. So if we're finding a difference in proportions, mathematically that means we're subtracting. So we're taking two separate proportions and finding the difference. So we got to think back to chapter 8, which was intervals. And so when we did intervals, we stated our population or our parameters and what we did it usually within, and we defined we want to estimate such and such. Now, because we've got two separate groups, usually I define the population within, but it's going to be beneficial to you to go ahead and define which one's which and with a symbol, so that we can kind of refer to them that way throughout. So we are going to define each of our two parameters. And I guess I should be doing colors because I usually am here. See if we can do this. And then proportion, however, I usually write it in context / population. So write that consistent to what you usually do. Of successes in population, something like that. Now, these right here, you don't need to write anything on this sheet, but I want to mention it because I always forget to. I'm just putting 1 and 2 because we don't know what they are. A lot of times people are going to use 1 and 2, and that's fine. That doesn't mean you have to use 1 and 2. Sometimes I use things that are contextual variables that are just going to like help me remember which one's which. If I'm dealing with males and females, to me, 1 and 2 isn't very helpful because then I'm going to have to remember every single time which one did I say is 1 and which one did I say is 2. So in that case, I would do like PM and PF so that it's very obvious to me which one's which. And then I could do let PM be the proportion of males that ... and so forth, and then do the other one as females. So you can change the subscript to be context if you want, or to be a letter if you want. Even if it's something like 2009 versus 2010, I could write 2009 here, 2010 here. It doesn't just have to be one number, one letter. All right, so we're going to keep this going like we usually do. So that is going to help me, but now we're going to do it like we had been doing. So we want to estimate. And so usually we estimate P or mu right here, but we're not estimating just the parameter, we're estimating the difference in. So we want to estimate the true difference in proportions. And so this part right here, I have to specify a direction. Probably should have written this color. And what I mean by that is, am I taking P1 minus P2 or am I taking P2 minus P1? Because everything's going to change in your problem based off of the direction that you subtract. So I'm basically specifying here which direction I'm subtracting. So the difference in proportions of, and then this is where we're going to put all of our context populations. And then we always end with number percent confidence. So the only thing that changes there is I want to go ahead and define what each of them are, and I'm doing the difference in proportions. I'm specifying the direction. So for plan, I always start with method. Well, you should be getting pretty close to this at this point. Now, we usually start with one sample. Well, now if we have a difference in proportions, we have two samples. So this is a two sample. Our option now is Z or T. We're doing proportions, so it's always Z. It's either a test or an interval. We're doing a confidence interval, so this is interval. And then now it's for difference in proportions instead of just for proportions. So the biggest thing about a two sample problem is every condition that we check, we have to check for both samples. So I'm just going to specify, I usually just write check for both, but people mess it up. So I'm going to try to do it this way. Population 1, population 2. Check random selection / assignment. So this would be something like problem stated females were randomly selected and problem stated males were randomly selected, or problem stated that both females and males were randomly selected. So you have to specify directly, this one is randomly selected, this one is also randomly selected. So you have to make sure you specify both. You can't just say the people were randomly stated, people were randomly selected. It has to be specific to both populations. So normal. So this is probably the one I want to hit on the most right now because of issues I've seen recently. We are dealing with proportions. So we cannot use central limit theorem. We do not draw a histogram. Our only method for checking for normality for proportions is some form of n times p. Now, sometimes n times p, sometimes n times p hat, sometimes n times p naught. So that's where we have to make our decision at this point. We are doing an interval, which means we are estimating a parameter. So am I given the actual parameter? No, which means I have to, by default, use what? I have to use p hat. But we have to check it for both samples. So I'm doing n1 times p hat 1. I'm doing n1 times 1 minus p hat 1. I'm doing n2 times p hat 2. And n2 times 1 minus p hat 2. And each of these have to be what? Greater than or equal to 10. Sometimes I just write that. But since this is your blank format, I'm going to go ahead and write all these out as greater than or equal to 10. But usually in my answer key, I just write a really big greater than or equal to 10, showing that all of them are. So then, just like before, now that I do this, I have to write out there are at least 10. And I'm going to show you ways that I do this to kind of make it easier. But I do want to specify for this. I'm going to say population 1 successes. Usually we don't have to write out this much. but I've noticed that some of you are not doing this part correctly, so I want to be specific. Population 1 failures, population 2 successes, and population 2 failures. And then we always have to end with, so we can use normal approximation. And then independent, which is still 10% condition. And we have to check this for both. So you're going to have capital N1 is greater than or equal to 10 times lowercase n1. And you're going to have capital N2 is greater than or equal to 10 times N2. And writing out there are at least whatever. And then so these are going to have different numbers. There's going to be 2 different ones. Sometimes. And we're always writing population here, not success, just a reminder. We need our different variables. We're going to have a p hat 1. We're going to have p hat 2. We're going to have an n1. We're going to have an n2. We're going to be given a confidence level because it is an interval. And we're going to find a z with that. Or z star, whichever we want to call it. So then our equation is going to be coming back to where we specified the direction here. We have to use that same direction here. So don't write this that I'm writing down here. This used to be our equation. For one sample. So we're going to look at this and then actually write the real equation. So instead of just having p hat, we're finding the difference. So whichever direction we specified, so the same as the specified direction from state, we still have z. And then now we have this, but we have it for both. So when you're adding the standard deviation of 2 independent random variables, you have to add them together, but you have to add them together in the state of variances. Well, this is square root. So how do I get variance? I square it. So I add them together. You don't have to erase that. I'm just showing you why this is. So I'm taking this variance, which is that squared. I'm adding it to this variance. But now I want to bring it back into the state of standard deviation, which means now I'll take a square root at the end. So that's why they're both together under there, is combining in the state of variances and then bring it back to standard deviation. Which I'll address that more in person if I need to. Most of you probably aren't even going to listen to me for that, but I want you to understand where it came from. So this does not go. And then conclude. Just like before, we are number percent confident. Again, why I'm making such a big deal about how starting at chapter 7 and 8, you've got to put in the effort on the front end and it will pay off because everything is still very repetitive. So we are blank percent confident that, and now instead of just the true proportion, the true difference in proportion which is that same specified direction. Make sure I match it the same way I did here. Of, and you're writing this to match like the way you wrote it here. And then we always end with will fall between our lower number and our upper number. And we're dealing with proportions, so we do not have units.